Welcome everyone. I am Yusuf Amar Khoja. We'd like to carry on solid geometry and topology. I started the last video proving what I called the new Euler's formula, and you can check that video and subscribe to my channel if you want to. Just check on YouTube. Yusuf is written here with CEF, Amar with two M's, Khoja, KHODJA. And it's rather good if you can watch the first video first, and then we can, this new video is about an application of those formulas. Let me recall those formulas, and this way we will go straight away to apply them to a football sphere, which is actually a polyhedron made of 12 pentagons and 20 hexagons. 12 pentagons and 20 hexagons. So the football is its components are 12 hexagons. I choose to make it more real, like here painted in black. Add to them 20 hexagons, white hexagons here. For example, for this football. That makes it 32 faces. I choose a provocative title for this video, which is the football and coronavirus geometry, because as you can see it here, actually polyhedra, you can find them as well in nature. You can see here the virus, the coronavirus 19. Look, it's very spherical, like a football. Add to that those coronas, I mean spikes, are almost situated at the top of vertices. Right. What I mean for the new viewers, I would like just to recall basic things about solids, about archemedien convex polyhedra or solids. What we call vertices, there are a number of corners. For example, here, take a cube. The cube has got 8 vertices. V equals 8, capital V. We use capitals for the 3D solids and lower cases for their net. So what we call a net, actually, back when I was a high school student, my question, that was back in 1988, was how to cut a cube, how many cuts you need to do on the cube to get the flattened nets. Like this cross, for example, just one of the 11 different nets of the cube. We do have another one, for example, the net that looks like this, for example. So I found out when I used the famous formula from Euler, from 1750, that he discovered in 1750, and you will see all those details in the last video. So I invite you to go and check on the first video about the new Euler's formula. So V number of vertices, E number of sides or edges, and F number of faces, which are 6 here for the cube, and 12 edges. When you flatten the cube, you get a pattern or a net. The most famous one is this cross, and as you can see here, those edges, those cuts here made edges on the corners here, and there are 7 cuts, and the other, so what you call cuts, C, is the number of cutted edges from the solid into its net. And you notice there are other edges that are not cutted, what we call folds, non-cutted edges, P. So P, let's call name P, number of non-cutted edges or folds of the net. So I discovered back in 1988 that C, number of cutted edges, it always equals to number of vertices minus 1. For example, for the cube, it's always 7, 8 minus 1. And the number of folds, it always equals to number of faces minus 1. For example, here, for the cube, number of folds is 5, 6 minus 1. You can check it here, for example. The folds are 1, 2, 3, 4, 5, and the cuts are 7. Now, there are other formulas that they are quite useful. The number of vertices on the nets, on any net, all the 11 nets from the cube or from any nets of a solid, convex archemedien solid, are always equal to 2 times the number of cuts. And these measure number of vertices, like here, for example, when you go around, number of vertices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here, V equals 14. It always even and equals 2 times number of cuts. Like here for the cube, 14 equals 2 times 7. We said for the cube that number of cuts is V minus 1, 7. Also, number of edges of the solid, it always equals to number of elementary edges when you take every face, every element of the solid, like here, for example, for the cube, we've got here 6 squares, and each square has got 4 vertices and 4 vertices and 4 edges. So a number total of edges, it always equals number of vertices, and you will see why in the last video. And it always 2 times the number of solid edges, 2 times. So V bar equals E bar and equals 2 times E, or E, capital E, equals V divided by 2 or E divided by 2. And from here we can notice straight away that V and V bar and E bar, they're always even on all the nets of a polyhedron. Now let's go back to our example for the football. So as you see here, we've got 12 pentagonal faces and 20 hexagonal faces. That makes it 32 faces. So we've got already that F equals 32. And from here, number of folds when you get the net makes P equals 31. Let's check it. I've got here a net of, you see here, this is a real football with hexagons and pentagons, black pentagons. This is the way that the pentagons, the hexagons are connected to a pentagon. And now this is one of the nets of the football skin. Let me tell you that the number of nets must be hundreds of thousands, many different shapes, because it's combinatory, and there are hundreds of thousands different permutation of those 32 faces. As you imagine, there are like factorials. When you use factorials, only if you, for example, you can check it on your computer, 32 factorials, that's a huge number. And so we should expect that number of different shapes of the football skin must be at least hundreds of thousands different of number of different shapes. Right, we just computed that number of folds for football is 31. Let's check it here. I can see one here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I try to do it row by row. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30, 31. So 31 folds on the football skin. P equals 31. Now, to find number of cuts, which is number of vertices here, without going to compute the vertices straight away, we can go, for example, to compute something easy straight away from those numbers here. We can compute number of edges of the football, number of edges on the skin of football. So, as we know that capital E equals E bar divided by 2, like here. And E bar equals 12 by 5 edges for each hexagon. Add to that 20 by 6 edges for each, I said here pentagon, and this is hexagon. So let's compute E. E bar equals 12 by 12 times 5. Add to that 20 times 6, which is 60 plus 120. That makes it 180 individual edges. So capital E, number of edges on the football, equals 180 divided by 2, which is 90. E equals 90. So let's call this result 1, this is result 2. We've got E equals 90 and P equals 30. There's another formula that was the original idea from the first video. I noticed when I was in high school back in 1988 that number of edges is always equals to number of cutted edges plus number of non-cutted edges. So we know that E equals C plus P. We've got E and we've got P, so we can compute C. That makes C equals 90 minus 31. Number of cuts, C football equals 90 minus 31, 59 cuts. Result number 3. So in the football net, when you cut the football and make it flat, you must have 59 cuts. You must cut this skin edge by edge, 59 different edges, and you will get as well, you have to have 31 folds, so non-cutted ones. 31 you leave them, and 59 you cut them. And of course, number of cutted edges, add to that to number of non-cutted edges, that makes the total of edges of a football, which is 90. 31 plus 59, 90. The other question that we can ask about this net, of course you can check the number of cuts here, but number of cuts actually the number of those flaps where you need to glue, because if you make a net or a pattern, a paper pattern to make a football, to like fold back a football, so you need to put those flaps here. Sorry, maybe it's too far for you. So you need to do those flaps on paper where to put a glue. So those little flaps, they are they are of number 59 on the football net. 59, and you can count them. You can go online and found those nets on Google nets of football. Right. So the other question that we can ask is, what is the length of the perimeter? What is the length of the perimeter? What I call a perimeter, actually, how many edges you have to go around. What is the length of going around this net? So I discovered that it's always even and equals 2 times the number of cuts. So V, what I call V here, V equals 2 times number of the cut, which is the perimeter. So from here, V equals 2 times 59, which is 118. V equals 118. Result number 4. So I would like you to go and check all those things, which is quite fun to do and a very good exercise for high school students, for example, and this is a good introduction to topology. You will see that in 1750 Euler found a great formula for that was the beginning of topology and graph theory, that says for any archemedien convex polyhedra or solid, number of vertices minus number of edges plus number of faces always equals to 2. And I invite you to go to watch my first video on Youssef Amar Hoja YouTube channel, and I thank you for subscribing and sharing this video. Thank you very much. I have other videos coming about geometry and very good things, fun things that unfortunately we don't teach in schools. And I try to make it as fun as possible and in same time serious mathematics. Ciao.